pedestal, cast it back down into the role of a mere tool, and firmly reseat the human being as the undisputed, messy, brilliant hero of the future.
Usually when we talk about a medical diagnosis, there's this underlying expectation of mechanical precision. It's almost like engineering.
Right, it's very binary.
Exactly. Like
Yeah.
if you fall and break your arm, you go to the hospital, they put you in an X-ray machine, and then, a few minutes later, you're staring at a jagged white line on a black background.
The doctor just points a pen at it and says, well, there it is. There's the problem.
Yeah, and it is incredibly comforting to have that. I mean, we fundamentally like things to be visible. We like them to be categorized and, placed in neat little boxes. We really crave the mechanical certainty of the X-ray machine.
But then you step away from the skeleton.
Right, you step into the world of neuroscience. You try to look at the inner workings of the human brain, and suddenly that metaphorical X-ray machine is just completely useless. We're looking at a diagnostic and theoretical landscape that is, honestly, it's incredibly murky.
Oh, absolutely.
It is not a clean break on a bone. We are dealing with billions of neurons firing in these complex cascading patterns that we barely comprehend.
Diagnostic muddy waters is honestly probably the most generous way to describe it. And because we as a society, and I mean specifically the scientific community, are so deeply uncomfortable with that murkiness.
Yeah, the sheer terror of it.
Right, the terrifying complexity of human cognition. Because of that, we've started looking for a shortcut. We want a new kind of X-ray machine.
We want an easy answer.
Exactly. We are desperately searching for a technological savior that can just, scan the incomprehensible murk of the mind and spit out a binary mechanical answer.
Which brings us perfectly to the mission that you and I are embarking on in today's deep dive. If you're listening to this right now, we're about to unpack a massive, almost unquestioned assumption that has completely taken over the scientific community over the last couple of decades.
It really has.
The assumption is basically this. If we just throw massive room-sized supercomputers and an absolute mountain of big data at the human brain, we will inevitably unlock its secrets.
That's the prevailing belief, yeah.
Right, that artificial intelligence is going to be the ultimate all-seeing X-ray machine for the mind. But the source material we are pulling from today, which is this deeply fascinating, heavily critical academic chapter titled AI Mythology, Invades Neuroscience. It systematically deconstructs that entire premise.
The author basically takes a sledgehammer to the foundational logic of modern neuroscience. We are exploring a highly controversial and, frankly, a deeply philosophical argument here.
Yeah.
The text argues that artificial intelligence isn't actually saving neuroscience. In fact, this blind reliance on AI and big data, well, it might be actively stalling the entire field.
Stalling it. Wow.
Yeah, it is freezing our understanding of the brain in place. We are going to look at how the culture of science has shifted away from the individual genius toward this concept of swarm science.
Which is a wild concept.
It is. And we'll dig into the spectacular billion-dollar failures of these massive government-funded big brain projects. We also have to mathematically unpack something called the mapping problem.
The math on that is going to blow people's minds.
Oh, definitely. And then we'll get into the very real, very dangerous statistical trap known as overfitting.
My level of curiosity is absolutely through the roof on this. Because fundamentally, we are talking about how a tool, which is, all AI really is, a highly advanced computational tool.
Right, it's just a tool.
How could that tool completely upend and rewrite the underlying philosophy of a totally different scientific field? It's like asking how the invention of the calculator changed the philosophy of biology. It just doesn't seem like it should.
It doesn't, no.
So let's unpack this. The text argues that to truly understand what has gone wrong in neuroscience, we first have to examine a massive philosophical shift in how we view the human scientists themselves.
Yeah, the text maps out a profound change in the scientific self-image. This isn't just an academic squabble over which software to use in a lab or who gets the most grant money.
Right.
It is a crucial debate about what constitutes actual scientific discovery versus just mere data collection. It's really a fight for the soul of the scientific method.
Okay, so who are the main players here?
Well, the author introduces us to Sean Hill. Hill was previously the director of the International Neuroinformatics Coordinating Facility.
Which is a mouthful.
Yeah, it's a massive collaborative effort that basically acts as the data hub for the Human Brain Project. Anyway, in a 2015 anthology titled The Future of the Brain, Hill wrote an essay outlining his vision for the future of scientific endeavor.
And what was his vision?
In this essay, he didn't picture lone, brilliant researchers having these aha moments in quiet labs. Instead, he pictured, and I quote here, swarms of scientists attacking the major challenges of understanding the brain.
Swarms. I have to pause on that word.
It's a very specific word choice.
That word choice is so deliberate, and honestly, it's a bit chilling when you actually visualize it. The author of our source text calls it an absurdly deflationary metaphor, and I think that hits the nail on the head.
Definitely.
When you think of a swarm, you think of bees or, like, ants.
Yeah.
You think of a hive mind where the individual insect is totally expendable.
Totally thoughtless, yeah.
Right, just operating on raw instinct to serve the collective mass. Hill talks about triggering a new wave of global collaboration, which sure sounds fantastic on a PR brochure for a grant application, but then he immediately reduces the incredibly brilliant, highly educated minds doing the actual work to essentially mindless insects.
The terminology strips away the agency of the individual, and this is not just an isolated slip of the tongue by one overenthusiastic researcher either.
No.
No, Henry Markram, who was once the visionary director of that same human brain project, he echoed this exact sentiment, perhaps even more aggressively.
What did he say?
He argued publicly that modern science is hampered by the romantic belief that we need an Einstein to explain how the brain works. Markram stated that what we actually need is for scientists to set aside their egos and create a new kind of collective neuroscience.
We don't need an Einstein. I mean, to look at the entire history of human scientific breakthroughs, Newton, Curie, Einstein, Hawking, and then to just confidently declare, yeah, we don't need that kind of intellect anymore. We just need a swarm of data gatherers.
The sheer audacity of that claim is just staggering.
It really is. And the author of the text traces this mindset back to the rise of Web 2.0 culture, right? It's the internet culture of crowdsourcing, totally bleeding into the scientific method.
Yeah, the text maps out that cultural evolution brilliantly. If you think back to the early days of Web 2.0, the initial promise of the internet was all about empowering the individual.
Like blogs and personal websites.
Exactly. User-generated content. You, the individual, have a voice. Then, as the technology matured and consolidated, the vision shifted toward connecting those individuals into massive collective groups.
So Wikipedia, Facebook, Twitter.
Right. The operating philosophy became this idea that the crowd is inherently wiser than the individual. And finally, the text argues, we have arrived at the current stage, which they call the AI inevitability mythology.
The AI inevitability mythology.
Yeah. This is the stage where the narrative shifts one final time, relegating human beings entirely to the sidelines. The humans are just the swarm feeding raw data into the machine, and the machine, this mega technology, takes the spotlight and is expected to do the actual thinking.
It totally diminishes human potential. I mean, it takes a scientist who spent a decade getting a PhD and turns them into a mere technician whose only real job is to format spreadsheets and feed data into an IBM supercomputer.
Which is incredibly insulting to the scientists.
Absolutely. And the text brings up Alan Turing, which I thought was a really fascinating historical counterpoint to this whole swarm mentality. Turing, famously working at Bletchley Park cracking the Enigma code during World War II, he's arguably the godfather of modern computing.
He literally laid the conceptual groundwork for the machines these neuroscientists are using today.
Exactly. But Turing fundamentally understood something that modern big data advocates seem to have completely forgotten. Computers don't have insights. People have insights.
Right, the machine just crunches the numbers.
Turing understood the absolute boundary between computation and cognition.
And the text emphasizes that this vital lesson has been entirely lost in the modern rush for AI. We are now actively disparaging the very concept of an individual Einstein just to make room to talk up the sheer processing power of our machinery.
It's sad, really.
We are subjugating human intellect to a computer-centric view of the world. In this new paradigm, the ascendance of machines is viewed as a historical inevitability, and individual human discovery is viewed as this ego-driven, inefficient relic of the past.
But logically, I have to push back on this swarm concept. I want to try an analogy here.
Okay, let's hear it.
Is treating fundamental scientific discovery like a swarm essentially the same thing as trying to write a brilliant, paradigm-shifting novel using Wikipedia's crowdsourcing model?
Oh, that's interesting.
Right. Think about it. If you have 10,000 people collaboratively editing a document, you will absolutely get a massive amount of information. You will get data. You will get perfectly fact-checked historical dates and, geographical references.
Yeah.
But do you get a narrative arc? Do you get the emotional resonance, the subtext, the aha insight that makes a novel brilliant? No. You get an encyclopedia.
You get a very dry reference manual.
Exactly. And an encyclopedia, no matter how detailed, is never going to give you a brand new theory of physics or a totally new understanding of human consciousness.
That is a phenomenal way to frame it because it highlights the exact limitation of the swarm. A crowdsourced swarm will give you a highly detailed description of what is already known, but it absolutely cannot make the intuitive, conceptual leap required to discover what is completely unknown.
Which is the whole point of science.
Right. And that is the exact critique the author is leveling at these modern big science projects. If scientists are reduced to a swarm of technicians simply crowdsourcing biological data, what exactly are they swarming around? What is the goal?
Yeah, what are they actually doing?
This leads us directly into the massive top-down engineering projects that have completely dominated neuroscience over the last decade. Because these leaders weren't just talking about swarms as a fun theoretical concept, they were actively convincing governments to put billions of dollars behind this philosophy.
Billions with a B.
Mm.
And we have to talk about the sheer scale of these projects, starting with the granddaddy of them all, the European Union's Human Brain Project.
The HBP.
This thing officially launched in October 2013, and the scope is just, it's hard to wrap your head around. We are talking about a 10-year initiative backed by a $1.3 billion award.
It's a staggering amount of money.
It involved over 150 different scientific institutions scattered all around the world, all supposedly working together in perfect harmony. And it was initially led by the very same guy who said we don't need an Einstein anymore, Dr. Henry Markram.
To truly understand the immense hubris of the Human Brain Project, you have to look at Markram's background and what made him famous in the first place.
Okay, what was his claim to fame?
He was previously known for a highly publicized initiative called the Blue Brain Project. The goal of Blue Brain was incredibly specific. Markram wanted to model an entire neocortical column of a rat's brain in silica.
In silica, meaning running the model entirely in a computer simulation.
Right, in this case on a massive IBM Blue Gene supercomputer.
Okay, let's slow down for a second for the listener, just to define what a neocortical column is.
Good idea.
The neocortex is the outer layer of the brain, right?
Yeah.
The part responsible for higher-order thinking, sensory perception, and motor commands. A cortical column is basically a tiny vertical slice of that outer layer. It's a very localized network of neurons.
Yep, that's exactly it.
So Markram was trying to perfectly simulate just one tiny microscopic slice of a rat's brain, which, to be fair, still sounds like an incredibly impressive computational feat.
Oh, absolutely. Modeling the electrochemical dynamics of even a single rat's neocortical column is a breathtaking engineering marvel. It required massive computational power just to simulate that one tiny slice.
Right.
But the Human Brain Project took that highly localized scope and exploded it to an irrational degree. Markram gave a now infamous TED Talk in 2009, where he stood on a global stage and publicly promised that with enough funding, his project would deliver a complete, fully functioning computer simulation of the entire human brain by the end of the decade.
By the end of the decade. He stood up in 2009 and said, give me the money, and by 2019, I will have a simulated human mind running on a hard drive.
Yes.
He wanted to go from a tiny slice of a rat's brain to the entire 86 billion neuron human brain in 10 years. And the craziest part is the European Union actually believed him. They gave him $1.3 billion to do it.
It became a massive geopolitical flex.
Oh, totally. And the United States wasn't about to be left behind in the dust. The source text notes that the Obama administration subsequently announced the BRAIN Initiative, which stands for Brain Research through Advancing Innovative Neurotechnologies.
Right, the U.S. response.
They dropped an initial $100 million in 2014, projecting up to $300 million over 10 years. You also had the Allen Brain Atlas, heavily funded in Seattle. It was this sudden global gold rush of big science.
It really was.
And they were all operating on this exact same underlying premise, right? Collect massive amounts of data, stuff it into a supercomputer, and the brain will just spontaneously reveal its secrets.
The assumption was that scaling up the data collection would inevitably scale up the theoretical understanding. And this raises the most important question of this entire deep dive: what actually happened at the end of that decade?
Did he do it?
Did Henry Markram deliver his simulated human brain in 2019?
Let me guess. No.
The text quotes Ed Young, writing a retrospective piece for The Atlantic in 2019, and he summarized the outcome brutally and succinctly. Young wrote, quote, "It's been 10 years. He did not succeed."
He did not succeed. That might be the understatement of the century.
It was a disaster.
The project was a spectacular meltdown. Confronted with massive mismanagement allegations, widespread internal revolts from the scientists involved, and zero progress toward a simulated brain, Markram actually had to step down as the head of his own project just a couple of years after it launched.
The mutiny was very real.
And then, as the text describes it, the project executed this incredibly shameless rebranding campaign. They quietly scrubbed the promises of simulating the human brain from their websites and just became a software infrastructure project.
Right.
They spent $1.3 billion just to become a catalog, providing IT tools and data sharing methods for other smaller teams of human scientists who are doing actual ongoing biological research.
It morphed into exactly what its most vocal critics warned it would be all along, a massively bloated, overfunded IT infrastructure project masquerading as fundamental biological science.
Wow.
But you have to ask why government agencies are so eager to throw billions of dollars at these projects in the first place, even when the underlying scientific community is highly skeptical.
Because it sounds good on TV.
Basically. The text points out that these big brain projects are incredibly good at pleasing politicians. They offer a very simple, easily digestible narrative. They promise practical, immediate benefits to voters.
Like curing diseases.
Exactly. They stand at a podium and promise to finally find the cure for Alzheimer's or to unlock the genetic secrets of schizophrenia and mental illness. George H.W. Bush declared the 1990s the decade of the brain. Obama had his brain initiative.
We just keep rebranding it.
We keep declaring these decades of the brain based almost entirely on the promise of technological deliverance rather than theoretical breakthrough.
Which brings up a massive glaring point of confusion for me and probably for anyone listening.
Okay, what is it?
If a $1.3 billion 10-year project misses its mark so drastically that the founder gets ousted in a mutiny and the entire initiative has to totally rebrand itself into a software catalog,
Yeah.
why on earth does the broader scientific community still cling to this exact same big data approach? Why are we doubling down on a philosophical methodology that just spectacularly failed on the world stage?
It seems entirely irrational from the outside, I know, but to understand why neuroscientists refuse to let go of this methodology, we have to look away from the politics and look directly at the sheer, terrifying mathematical scale of the organ they are trying to study.
The brain itself.
Right. They cling to big data and artificial intelligence because the traditional scientific alternatives seem mathematically, physically impossible. This brings us to a concept neuroscientists call the mapping problem.
Okay, let's really get into the math here, because the numbers presented in this chapter are actually mind-bending. It requires a total shift in perspective.
They really do.
The Kavli Foundation put out a comparison that really stuck with me. They said that just measuring a tiny microscopic fraction of the neurons in a single mouse brain could generate as much raw data as the Large Hadron Collider.
Which is insane to think about.
It is. And just for context for you listening, the Large Hadron Collider is a 17-mile-long, multi-billion-dollar physics machine spanning the border of France and Switzerland that smashes subatomic particles together to hunt for the building blocks of the universe.
It generates an absurd amount of data.
An absurd amount. And yet, a tiny fraction of a mouse brain equals the data output of the largest, most complex machine humanity has ever built.
The scaling is almost incomprehensible. Amy Kennel, writing in the journal Biomed Central, pointed out that neuroscience is very quickly going to far exceed genomics as a data-intensive science.
Really? More than the human genome?
Oh, easily. For a long time, mapping the human genome was considered the absolute heavyweight champion of biological data. But Kennel notes that current supercomputers, which run at what is called the petascale, are simply not powerful enough to handle the data output of the brain.
They need something bigger.
The Human Brain Project and initiatives like it require a jump to exascale computing. They're literally having to fund the engineering and development of entirely new tiers of supercomputers just to hold the data they want to collect.
Oh, okay. Let's actually define those terms for a sec so they don't just sound like sci-fi jargon. When we talk about petascale computing, we are talking about a computer that can calculate 1 quadrillion operations per second. A quadrillion is a 1 with 15 zeros behind it. That is the current state of the art.
Right.
But Kennel is saying that's not enough. They need exascale computing. An exascale computer can calculate 1 quintillion operations per second, a 1 with 18 zeros, a billion calculations every single second.
It's hard to even picture that.
And they need this entirely new, barely invented tier of technology just to hold the data of a small brain.
And to truly understand why they need a billion billion calculations a second, we have to walk through the underlying math of the human brain, which is broken down beautifully in the text by Rebecca Golden for the Genetic Literacy Project.
Okay, let's hear the math.
This is a step-by-step logical progression that really highlights the impossibility of the task. Step 1, the average adult human brain contains an estimated 86 billion neurons.
Okay, 86 billion. That's roughly equivalent to the number of stars in our Milky Way galaxy.
Yeah.
So you have a galaxy of neurons in your head.
Right. Now, step 2, each one of those 86 billion neurons doesn't just sit there in isolation. They reach out and connect to other neurons. A single neuron can have tens of thousands of synaptic connections.
Wow, tens of thousands.
Yeah, these synapses are the tiny chemical gaps where neurons pass signals to each other. Step 3, if you multiply 86 billion neurons by tens of thousands of connections, you arrive at more than 100 trillion neuronal synapses in a single human brain.
100 trillion conversation sites constantly buzzing with activity.
Exactly. Now, imagine you are a neuroscientist and you want to record the simplest, most basic, stripped-down piece of binary data possible for each one of those 100 trillion synapses.
Okay, like a 1 or a 0.
Yes, you don't care about the chemical makeup, you don't care about the voltage strength, you just want to know, did it fire or did it not fire? A simple 1 or a 0. If you wanted to record that binary state in a specific time window for all 100 trillion synapses simultaneously, it would require 100 terabytes of data storage.
100 terabytes just to take a single frozen snapshot in time of a binary yes or no state.
Just one snapshot.
But the brain doesn't stop. It's dynamic. So Golden takes this math further. She calculates the storage needed to record that incredibly simple binary information continuously every single second over the course of just one day.
Just 24 hours.
Just 24 hours. And just for one single person. That continuous recording would require 100,000 terabytes. Or, to use the larger metric, 100 petabytes of raw data for one person. For one day.
It's massive.
And the author of our source text makes sure to point out that the most powerful supercomputers in the world right now hold about 10 petabytes.
The data requirements instantly dwarf our physical hardware limits. But here's the kicker. Here's where the mapping problem transitions from really, really hard to truly intractable.
Oh, there's more.
Yeah. That 100 petabyte figure, that only accounts for a totally static brain. It assumes the 100 trillion connections never change, but we know they do. It completely ignores neuroplasticity.
Right, because we learn things.
Exactly. Every time you learn a new skill, every time you form a memory, every time you get a good night's sleep, those synaptic connections physically change. They grow stronger, they weaken, they physically move and connect to different neurons.
So the map is constantly redrawing itself.
Yes. If you want a computer to trap how those connections physically change their structural positioning and connectivity over time, the data requirement explodes exponentially. It amounts to a data figure with more bytes than the estimated 10 to the 80th power atoms in the entire observable universe.
More bytes than there are atoms in the universe.
Let that sink in for a second. That is the true scale of the mapping problem. It's a wall of sheer magnitude.
It really is.
And honestly, when you look at that wall, when you realize that mapping the brain requires more storage than there is physical matter in the universe, you suddenly start to understand why guys like Henry Markram are so desperate.
You really do. You understand why they start promising the impossible. Because mapping the wiring of the brain manually, testing hypotheses one by one, or even with traditional petascale computing, is literally impossible.
It just can't be done.
So they are backed into a corner. Markram argues that because the wiring problem is mathematically intractable, relying on artificial intelligence and massive data integration are literally the only viable paths forward. He believes we have no other choice.
The scale of the brain forces a critical pivot in their scientific logic. Because human beings cannot possibly parse more bytes than there are atoms in the universe, these scientists surrender the task entirely to the machine.
They just hand it over.
Right. They hope that by feeding this incomprehensible ocean of unorganized data into a highly advanced AI, the machine learning algorithms will magically discover the hidden statistical principles of the mind.
Just find the pattern for us.
They want the AI to figure out how these microscopic, tiny microcircuits connect to the larger functional macro regions of the brain. They are openly expecting the AI to act as a substitute for human-generated scientific theory. They are crossing their fingers and hoping the machine will just hand them the answer to consciousness.
And that exact expectation that the machine will just print out the theory of the mind if we feed it enough data, that brings us to the absolute core academic and philosophical critique of this entire text.
Yes. the heart of the matter.
The author argues that this approach fundamentally mistakes engineering for scientific discovery. It is a profound confusion between two totally different modes of logic, induction and abduction.
This is the philosophical heart of the argument, and it is vital to untangle these concepts. The text states very clearly technology is downstream of theory.
Meaning what, exactly?
What that means is that you build the technology after you understand the science. But in neuroscience right now, information technology, AI, supercomputers, exascale servers is being used as a replacement for actual intellectual innovation.
The cart is before the horse.
Exactly. The author labels this the conceit of AI mythology. It is the deeply flawed, almost religious belief that scientific theories that are completely unknown to us at the micro level will simply pop into existence on their own, provided we feed enough raw data into machine learning algorithms.
It's the idea that data automatically creates theory all by itself. Now, the advocates of these big brain projects almost always point to the Human Genome Project to justify this approach.
It's their favorite defense.
They say, look at the Genome Project. We successfully mapped human DNA using massive amounts of data and supercomputers. It was a triumph of big science. Why can't we do the exact same thing with the brain?
But the text absolutely destroys that parallel.
It really does. The author points out that comparing the Brain Project to the Genome Project is a false equivalent. And it all comes down to theoretical groundwork. The Genome Project was an engineering project from day one. It was not a theoretical discovery project.
The distinction is everything. When the Human Genome Project officially started, the foundational theory of DNA was already firmly established.
Right, Watson and Crick.
Yes, Watson and Crick had already discovered the double helix structure decades earlier. The scientific community already understood what base pairs were. We knew how DNA worked theoretically and mechanically.
So they weren't discovering how it worked, just what it looked like.
Exactly. There were no major missing pieces of theoretical biology blocking the path. The challenge of the Genome Project was simply the mechanical, repetitive labor of mapping it all out. It was a massive scaling up of a completely known process.
Right, they had the blueprint, they just needed to count all the bricks.
Exactly, but neuroscience does not have that blueprint. We do not actually have a foundational theory for how the brain generates consciousness or memory or general intelligence. Neuroscience has massive, gaping theoretical holes blocking its path.
It makes complete sense. You can't just engineer a bridge if you haven't discovered the laws of physics yet. You don't know what load bearing means.
You just be piling up steel.
But that is exactly what they are trying to do with the brain. And to bypass the fact that they don't have a blueprint, they are relying heavily on something called predictive neuroscience.
Right, predictive neuroscience.
The text breaks this down beautifully. Predictive neuroscience uses deep learning and AI to guess the unknown synaptic links based on the known ones. And on the surface, it looks like it actually works. The text mentions that Henry Markram had some significant success with this in his earlier models.
He did.
Using something called an F-measure statistic, his machine learning algorithms achieved nearly 80% accuracy in predicting the connections in a rat's brain.
Let's pause and define that F-measure statistic for a moment, just so we understand what Markram is actually boasting about.
Okay, lay it on me.
In statistics, evaluating an AI's accuracy isn't always straightforward. You have precision, which means out of all the connections the AI guessed were there, how many were actually real?
Okay, precision.
And you have recall, which means out of all the real connections that actually exist, how many did the AI successfully find? The F measure is basically the harmonic mean of precision and recall. It's a balanced score.
Got it.
And achieving an F measure of 80% means the algorithm is quite good at spotting statistical patterns in the data it was fed.
Now, I have to jump in here and play devil's advocate for the neuroscientists. Because to the average person, and honestly to me, 80% accuracy sounds pretty incredible.
It does sound high.
Right. If a machine is blindly guessing how a highly complex biological brain is wired, and it gets it right 8 out of 10 times purely based on statistical patterns, that feels like a massive win for AI.
Yeah.
Why is the author framing this 80% accuracy as a negative thing? Why does the text dismiss this as a failure?
Because you have to look at the devastating reality of the remaining 20%. You have to consider the context. We aren't trying to predict what movie someone wants to watch on Netflix, where a 20% error rate just means a bad recommendation.
Right, the stakes are higher.
We are talking about a biological system that is precise, fragile, and highly optimized by millions of years of evolution. In that context, an average error rate of 2 in 10 is absolutely catastrophic.
Wow, Catastrophic.
Imagine a cardiovascular surgeon operating with an 80% accuracy rate of cutting the right artery.
Yeah, that patient is dead.
Or imagine an aviation engineer building a commercial airliner where 20% of the wiring is just randomly connected based on a statistical guess by an AI. The plane will crash. If your ultimate goal is to reverse engineer a perfectly functional, biologically accurate human mind, a 20% error rate means you have built a profoundly broken, highly dysfunctional model.
It's like trying to translate a masterpiece novel from French to English, and every fifth word is just completely wrong. You might get the gist of a sentence here or there. You might understand that two people are in a room, but the overarching narrative, the subtle nuance, the actual meaning of the book is completely destroyed by the errors.
The errors compound until the model is useless. And what this 20% error rate truly demonstrates is the shallow logic of relying purely on inductive machine learning.
Induction versus abduction.
Exactly. This goes back to induction versus abduction. Induction is drawing generalized conclusions from specific data points. The machine looks at 100 neural connections and says, based on this pattern, connection 101 should probably look like this.
But it doesn't know why.
But it has no idea why. It lacks abduction. Abduction is the human ability to form an explanatory hypothesis. It's the ability to look at a wet driveway and hypothesize that it rained, rather than assuming someone dropped 1,000,000 glasses of water.
Right. Common sense, basically.
Abduction is the ability to say, these connections exist because of this underlying biological rule. Because the AI lacks that foundational theory of why the connections exist, it will inevitably make massive structural errors when trying to predict a system as complex as the brain.
So if we want to see what happens when big data is actually used correctly in science, when technology and theory work together the right way, using abduction and deduction rather than just blind induction.
Which is possible, by the way.
Right. The text says, we need to leave neuroscience for a minute and look at the world of physics. Specifically, we need to look at the discovery of the Higgs boson.
This is a vital comparison because it proves that the author isn't just anti-technology. The author acknowledges that big data can work wonders if applied correctly. In 2012, scientists at CERN used the Large Hadron Collider to discover a long-missing piece of the physical universe, the Higgs boson, which is the particle that accounts for mass.
And just like the big brain projects, this experiment involved an incredibly incomprehensible amount of data.
Oh, massive amounts.
The data output is staggering. The text notes that in 2012, when they discovered the Higgs, the collider generated about 25 petabytes of data in a single year. And by 2018, that had doubled to 50 petabytes.
That's a lot of hard drives.
The author says that's equivalent to about 15 million high-definition movies. So nobody is denying that big data analytics, massive server farms, and heavy computing resources are absolutely necessary for this kind of advanced science. It gives physicists incredibly powerful tools.
Tools being the key word.
Right. But here is the million-dollar question that the text poses. Why did physics succeed with big data while the human brain project failed so miserably?
The answer comes down to one man, and the timeline of his ideas, Peter Higgs. Peter Higgs proposed the theoretical existence of this particle in 1964. 1964, decades before the internet existed, let alone exascale supercomputers and machine learning algorithms. The physicists at CERN in 2012 weren't just turning on the Large Hadron Collider, smashing random atoms together, collecting 25 petabytes of unorganized data, and hoping a brand new theory of the universe would magically emerge from the algorithms.
They already had the map. They had been holding onto the map for nearly 50 years.
They had the map, and it was called the Standard Model of Particle Physics. They were conducting a highly specific, painstakingly controlled experiment, specifically designed to confirm a robust, pre-existing theoretical framework.
They knew what they were looking for.
They knew exactly what parameters they were looking for, they knew what energy levels to probe, and they knew what the data signature of the Higgs would look like before they even turned the machine on. The technology was used to test human insight, not to replace it.
So if I'm understanding this core argument correctly, big data is basically the world's most powerful magnifying glass.
That's a good analogy.
The physicists at CERN use that massive magnifying glass to look for a very specific set of footprints that they had already hypothesized would be there. They knew the shape of the boot, they knew the depth of the tread.
Right.
But the neuroscientists, they don't have a hypothesis. They're just dragging that exact same magnifying glass across a massive, endless desert, hoping the random grains of sand naturally spell out a map of the human mind.
Dragging a magnifying glass across the desert, hoping to find a map, that captures the futility perfectly. And what's truly astonishing, what really drives the author's critique home, is that the neuroscientists themselves openly admit this is what they are doing.
They admit it.
Yes. The text references a highly revealing interview in Nature magazine. This wasn't some fringe publication. It featured some of the most prominent neuroscientists in the world. Erik Kandel, Raphael Joust, Christoph Koch, Paul Matthews, and Henry Markram himself.
The heavy hitters.
In this interview, Paul Matthews openly admits, quote, "We do not have a strong paradigm to guide inquiry." He admits that these billion-dollar brain projects are merely big data collection exercises from which meaningful relationships are anticipated to emerge.
Anticipated to emerge. Just dragging the glass and hoping the sand spells out a coherent sentence.
And Markram doubles down on this mentality. In the same piece, he states that the more data we have, the more accurate the models will become, and he explicitly says he wants to use raw data to, quote, "fill the large gaps in our knowledge."
He is proudly putting the cart before the horse on a billion-dollar scale.
He is openly validating the author's exact critique. He admits he is relying on sheer computational power to generate theory from scratch. And this leads us to the most dangerous statistical consequence of dragging that magnifying glass across the desert without a map.
Which is?
When you do that, according to the top statisticians in the world, you don't find hidden maps. You find mirages.
Mirages. Okay, here's where it gets really interesting, because we move from the philosophy of science into the hard mathematics of why this fails.
The math doesn't lie.
If you just collect massive amounts of data without a guiding theory, your AI is inevitably going to start seeing things that aren't really there. The text introduces Michael Jordan, and to be clear, not the basketball player.
No, not the basketball player.
This is the IE Fellow and Distinguished Professor of Computer Science and Statistics at UC Berkeley. He is widely considered one of the world's top authorities on machine learning, and he issues a massive, flashing red warning light to the scientific community. He says society is about to experience an epidemic of false positives.
Jordan's explanation of this phenomenon is incredibly lucid and should honestly be required reading for anyone in science. He says that when you have large amounts of data, your appetite for finding hypotheses grows. You want to find connections.
Naturally.
But if the volume of your data is growing faster than the statistical strength of that data, then your inferences are going to be overwhelmingly false. They become white noise. He gives a fantastic analogy to explain this.
What's the analogy?
He says if you give him any massive data set, say, a database with millions of columns of random information, he can find some combination of columns that will predict any outcome perfectly just by pure random chance. He says it's exactly like the old adage of having billions of monkeys typing on keyboards. Eventually, purely by accident, one of them will write the complete works of Shakespeare.
But the monkey doesn't actually understand Shakespeare. It doesn't know what a sonnet is. It's just a statistical inevitability of having that many monkeys in that much time.
Exactly.
If you generate enough random data, patterns will eventually emerge by sheer coincidence. This brings in Nate Silver, the famous statistician and author, who defines this exact problem in his work. It's called overfitting.
Overfitting.
And we need to explain overfitting clearly because it is the Achilles heel of big data. Overfitting is when an AI spuriously matches data points to a description that has absolutely no genuine explanatory or predictive power.
The model basically memorizes the data.
Right. It works perfectly 100% of the time for the data you already have, but it is completely, spectacularly useless for predicting any new unseen data in the real world.
To ground this in reality, the text walks through a real-world failure of overfitting, and it perfectly illustrates the danger. The author brings up the catastrophic failure of a Russian mathematical geophysicist named Vladimir Kailas-Buruk and his student David Bowman.
Oh, the earthquake story.
Yes. In 2004, they attempted to predict a major earthquake in the Mojave Desert in California. They built this elaborate, opaque, highly complex statistical AI model based on historical earthquake data. They fed it decades of seismic readings.
Lots of data.
And looking backwards in time, their model perfectly fit all the past data. It could quote-unquote predict every earthquake that had already happened. It looked like an absolute stroke of genius.
They thought they had cracked the code of the Earth. But when it came to predicting the next earthquake, the unseen data in the future, the model failed miserably. The earthquake didn't happen when they said it would, and it didn't happen where they said it would. It didn't work.
It completely whiffed.
And David Bowman, exhibiting a very rare bit of scientific humility in this space, admitted exactly why it failed. He admitted the model was overfit. It failed because they relied purely on statistical correlations and lacked a true theoretical geological understanding of what was actually happening under the Earth's surface along those tectonic fault lines.
They didn't understand the why.
Because they didn't have a causal theory guiding their math, a theory of why the plates move. Their AI model just picked up the random, meaningless noise of past earthquakes and mistook it for a predictive signal.
It's the ultimate inescapable trap of big data. Without a foundational theory of causation, the machine simply cannot distinguish between a meaningful biological pattern and a totally random coincidence.
Right.
The text provides a hilarious but terrifying example of this from researchers Marcus and Davis. They point out that if you run a big data analysis on the years 2006 to 2011, you'll find a sharp, undeniable, statistically perfect correlation between the United States murder rate and the market share of the web browser Internet Explorer.
That is insane.
Both of those metrics went down sharply at the exact same time. The AI would look at that and say they are inextricably linked.
Which is completely absurd. Internet Explorer, losing market share to Google Chrome, did not cause people to suddenly stop committing murder. It's a perfect statistical correlation with absolutely zero causation.
Zero.
So let me ask you to explicitly tie this Internet Explorer analogy back to the Human Brain Project and the current state of neuroscience. If we apply this Internet Explorer logic to a $1.3 billion simulation of the human mind, what is the actual tangible risk to the science?
Yeah.
Are we just going to get billions of dollars worth of perfectly correlated nonsense about how our neurons fire?
The risk is total scientific derailment. And yes, it is a near certainty if the methodology doesn't change. Without a causal theory, without a true abductive understanding of the biological and physical rules of general intelligence, these deep learning networks will simply memorize the noise of the brain data.
They'll just overfit it.
They will overfit the model. They will find millions upon millions of spurious correlations, just like the murder rate and the web browser. The algorithm might declare that a specific neuron firing in the motor cortex is perfectly correlated with a specific synapse firing in the visual cortex.
And it might be true in the past data?
And it might be true in the historical data, exactly, but it will offer absolutely zero insight into why they fire or how they work together to generate a human thought or a memory or an emotion. It will be a perfectly overfit billion-dollar model of biological white noise.
A perfectly overfit model of white noise. That is a devastating critique of the entire technological paradigm. Which brings us to the culmination of the author's argument, the ground-up illusion, and the stall of science.
The big finale.
If we have categorically proven that pure data and AI cannot generate theory on its own, where does that leave the actual human-generated theories in neuroscience today? What is the current state of our understanding of the brain?
It leaves neuroscience in a very precarious, very weak state. The text is fair. It acknowledges that neuroscience does have some good low-level theories.
We know a few things.
We do. We understand the mechanics of spiking activity in individual neurons. We understand ion channels, the literal biological gates that open and close to let sodium and potassium into a cell to create an electrical charge.
Okay, the small stuff.
We also have some understanding of what are called mesa circuits, which are the mid-level neural networks that connect small groups of neurons together. But the high-level theories, the broad theories of cognition, consciousness, and general intelligence that are supposed to explain how the entire neocortex generates a functioning mind, they are, in the direct words of the text, hopelessly general and unusable.
Hopelessly general. They can explain the individual brick, but they have no idea how the cathedral stays standing.
That's exactly it.
And here is the author's final, truly depressing conclusion about why this theoretical vacuum exists. The advocates of these massive data brain projects have essentially given up on human discovery.
They really have.
They are actively handing over the heavy lifting of scientific discovery to the supposed magic of AI. They genuinely believe that AI will eventually solve the mystery of general intelligence from the bottom up.
From the ground up.
They think the computer will start at those tiny ion channels, build up an understanding of microcircuits, then scale up to the mesocircuits, and finally, magically, present a working model of whole brain regions.
And because they believe the machine will do all this hard theoretical work for them, the human scientists are currently accepting a pale, incredibly weak set of theoretical postulates. They aren't pushing for new Einstein-level breakthroughs because they think the computer is about to do it for them.
It creates a self-fulfilling prophecy of scientific stagnation. But the author points out that it actually gets worse. Not only are the scientists accepting weak theories, but the high-level theories in neuroscience are increasingly contorting themselves to conform to the computing paradigm rather than to biological reality.
This is the scariest part.
Because they want to run the brain on a computer, they are starting to theorize that the brain is a computer. They are trying to make the biological brain fit the digital constraints of their supercomputers rather than doing the hard work of making the computer understand the messy, non-binary reality of the brain.
So what does this all mean for the big picture?
Right.
Stepping back and looking at the macro-level damage to the field of science. The mythology of AI isn't just failing to crack the code of the brain. It is actively undermining the traditional, historically proven process of scientific discovery.
Undermining it entirely.
By dumping billions of dollars into top-down, engineering-focused simulations of existing knowledge and simultaneously ignoring and defunding targeted, hypothesis-driven human discovery, we are effectively freezing our understanding of the human mind in place. We are stalling science in the name of technological progress.
We are replacing the pursuit of fundamental knowledge with the pursuit of data processing power. We have sidelined the theoretical Einstein in favor of the data-gathering swarm.
We have elevated the IT technician over the biological theorist.
And most dangerously, we have allowed the dazzling illusion of massive computational power to mask a profound, ongoing deficit in our actual biological understanding of who and what we are.
Absolutely.
Okay, we need to bring you, the listener, back to the surface after that deep dive. We have covered incredible ground today. We started with the chilling cultural shift away from the individual genius and the rise of the mindless data swarm.
We did.
We walked step by step through the staggering billion-dollar failures of geopolitical projects like the Human Brain Project, which promised a digital mind and ultimately just delivered a software catalog.
A very expensive catalog.
We did the math on the sheer terror of the mapping problem, realizing that recording the dynamic brain requires a dataset larger than the atoms in the universe. We contrasted the brilliant triumph of theoretical physics and the Higgs boson with the theoretical vacuum of modern neuroscience.
And finally, we unpacked the statistical mirages of overfitting, where AI gives us flawless correlations that mean absolutely nothing in the real world.
The core relevance of this journey and why it matters to you right now is that as we as a society continue to pour billions of dollars into big tech and artificial intelligence, we have to desperately remember that computational power is just a tool.
It is an incredibly powerful tool designed to test human ideas. It is not, and mathematically cannot be, a replacement for human insight.
Technology is downstream of theory. When we forget that fundamental rule, we stop doing actual science and we just start building incredibly expensive statistical mirages.
That's the real danger here.
And that leads to a final provocative thought that I want to leave you with today. A question to mull over on your own that builds on everything we've discussed. If our top scientific minds are increasingly trying to model the human brain exactly like a supercomputer, and they are relying almost entirely on AI to fill in the theoretical blanks they don't understand, are we eventually going to stop learning how the human brain actually works?
It's a scary thought.
Will we instead just force ourselves to believe that our minds are nothing more than biological machines, simply because that's the